Yeah, good evening, everyone. Let's start off. So, I hope everyone has gone through the notes. So, we'll be starting off with capacitors and current today. Again, quite an important one. Yeah, other scams on. Let's start off. Let's start off with a decent one. So, we have two capacitor plates, charge Q1, Q2. There is a switch here. Areas A, distance is D between them. Find the heat produced when the switch is closed. So this is Q and 2Q, and this is the ground there, and same story here. Find the heat produced when the switch is closed. This is a concentric spherical concentric shells. Get them both. I'll give another minute for both. They're not tough. If you've gone through the notes, you would have seen them. They're like standard ones. The first one is little. They both are based on Gauss law plus capacitors. So the first thing, right, when you say Q is equal to CV, so what is Q exactly there? When you say Q is a charge on a capacitor, are you talking about the total charge on the capacitor, or are you talking about the charge on the positive plate? So what is that Q exactly? So the thing is, when you say Q, understand one thing. What's a capacitor? So capacitor is not the plates. Capacitor is the region where the field lines are stored. So from Gauss law, we know the charge distribution here. The outside charge will be Q1 plus Q2 by 2. Q1 plus Q2 by 2. So this is before the switch is open. And here the charges will be Q1 minus Q2 by 2. And this is minus Q1 minus Q2 by 2. So now ask yourself, who is creating the potential difference between these two plates? This electric field. This electric field is responsible for the potential difference between the plates. And this field is created by this charge Q1 minus Q2 by 2. Right. So actually, if you see the derivation there, so E is nothing but Q1 minus Q2 by 2, that is charge by area, right? That is your sigma by 2 epsilon into 2, because there are two plates. So you solve this thing, and then that is where you derive this from actually. Right. So that would be V by D, and you'll get it. So the capacitance, right? So when you say charge on the capacitor, it is actually the Q is that Q1 minus Q2 by 2. Getting it? So I'll just leave it like this. So this is the field between the plates. So in the formula, when you write Q is equal to CV, this Q is the charge on the inner surface of the positive plate. So, or you can say the charge is responsible for creating the potential difference between the plates. You guys should have gone through the notes. It's the first question in the capacitor. Right. So, and when you close the switch, what happens? There is no potential difference. That means the charge, there should be no electric field between them. So this should become zero. This should become zero. The outside charges are unaffected. So simple question. So what happened to the energy then? So energy is nothing but U initial minus U final. U initial is Q square by 2C, which is Q1 minus Q2 by 2 whole square by 2C. That's your initial energy minus 0. That's your heat produced, and capacitance is A epsilon by D. Is that clear, everyone? So the energy stored in a capacitor is Q square by 2C. So the question is, what is that Q? Will you take Q1? Will you take Q2? Will you take Q1 plus Q2? So exactly what are you taking there? Clear? So the whole question is about that one discussion, like what is in the formula Q is equal to CV, what is Q? Clear with this? So the Q is not the total charge, because see, you generally don't have a problem, because Q minus Q, now, you know what used to happen? If it is Q minus Q, you used to get 0, 0, Q minus Q. So it was like clear. The charge on the inner surface is the charge on the positive plate. So yeah, just be careful with that. Not a difficult one, but yeah, it's a little important one. What about this guy? Same story. So first you need to find the charges before the switch is closed, then find the charges after the switch is closed, and then you can figure out from there. So before you close this thing, what are the charge distributions? This is Q, this is minus Q, and this should be 3Q. So you can treat this as actually two capacitors. So this is a C1 capacitor, this is a C2 capacitor. So C2 is a capacitance between the outer shell and infinity. So your infinity is your second shell. So this is one region and this is one region. From 2A to infinity. And I hope you remember the capacitance ka formula for spherical capacitor. 4 pi epsilon R1 R2. So that's 2A by 2A minus A. For a single shell capacitor, it is simply 4 pi epsilon radius. So luckily, I think you'll get the same thing. Both are equal. So when you ground the inner shell, so the moment you grounded this, so what is the new charge distribution? You have to figure out the new charge distribution. Let this be Q. Be careful. Just because you ground something doesn't mean the charge will become zero. Potential becomes zero. If this is Q, this is minus Q, the outer shell ka charge still has to be conserved. So this guy is 2Q plus Q. So if you try to find the potential at this point here, it should be 0. So VA is equal to KQ by A plus the total charge on the outer shell is 2Q by 2A must be equal to 0. From here, you'll get Q is equal to minus Q. So yeah, so that means your final charge distribution would be, this is minus Q, and this is 2Q. This is also Q. So that's your final charges there. Let's put the picture again. So after grounding, you'll get minus Q, you'll get plus Q, and this is plus Q. You're done. So what is the final energy? So this capacitor ka charge is Q and this capacitor ka charge is Q. Q square by 2C1, Q square by 2C2. What is the initial energy? Q square by 2C1 plus 3Q whole square by 2C2. Subtract them, that will be the heat produced. Are you clear with this? So this can be done using capacitors. There is another way to do this thing using self energies. If you remember, but that will be little lengthy because this is what will happen. You'll have self energy of this shell, self energy of this shell, self energy of this shell. So there are three self energies. Then interaction between these two energies, interaction between these two, interaction between these two. So there'll be three interactions. Totally, you'll get 6 terms. Can be done, but it becomes lengthy. So, but using capacitor, you can just finish it off. Clear with this? Something again similar to this, again Gauss law, and like I said, the end of Gauss law is the beginning of capacitors. And you can have a lot of questions based on both. So let's say we have an ammeter here. Mostly on Wednesday we'll be doing electrical instruments and devices. Today we have enough work. So let this distance be d and let this distance be d. I could change the numbers, but this is q, this is minus 2q, and this is 3q. Hope you guys remember these are three things. Now, this center plate here is oscillating in SHM. X is equal to a sine omega t. The middle plate oscillates in SHM. Find the current in the ammeter. Yeah, actually, I could have kept some, non-conducting springs here, and I could have pushed it, and I could have played around. I could have brought SHM also there. That would have been fun, but okay. I gave you the SHM part. So this ammeter which is there, what will be the reading of that ammeter? The A is less than D, so you don't go and collide with the plates. So we have three parallel plates. Initial charges are Q, minus 2Q, 3Q, and you have connected an ammeter there, and yeah. And this guy starts oscillating. Find the reading of the ammeter. If your cams are not on, you'll be removed from the classroom. So please do keep your cam on. Just get me the equation and then just say, okay, if we differentiate this, we'll get it. So don't worry about the mathematical calculations. Get me the main equation and you can leave it there. So main thing is that, like, how do you start something? So which concept should we use? If you guys remember, we did actually something like this. Yeah, remember I taught you this concept? Gauss law, I told you to revise this concept. X into D is equal to Y into D. You need to know that. X1 D1 is equal to X2 D2. So let's say when this thing is oscillating in SHM, what happens? The distance would change. This distance will become D minus X. This distance will become D plus X. Then the charge distributions will be, first of all, what is the charge outside? Outside charge will be total by 2. Total is 3q plus q minus 2q. So the total charge will be q and q. Great. So if you take this thing as q, small q, this has to be minus q. This is the second result. The facing plates will always have equal and opposite charge. If this is q, then this guy will be minus 2q minus q because the central plate ka charge is conserved. If this is minus 2q minus 2q, then this guy will be 2q plus small q. Right? And then we also have a relation, this q into this distance and this q into this distance is constant. So q into d plus x is equal to minus of 2q plus q into d minus x. You can simplify this. So this will be qd qx minus 2qd plus 2qx minus qd plus qx. So yeah, you can solve this and you will get the value of small q from here in terms of x. How much will that be? qd 2qd is equal to 2q x minus d. So 2q is equal to q by small d x minus d. I think I'm right. I could have done a mistake. Check it out. So we got the small q from there. Then how do you find the current? Ask yourself, if you assume the current I is flowing this way, so current is nothing but dq by dt. So what is q exactly? The total change in charge of whatever is the system. So the rate of change of charge on this plate must be equal to the current. So I must be nothing but rate of change of charge, which is q plus 2q plus small q. So yeah, and then capital Q is anyway constant. So I is equal to dq by dt. You can differentiate this and you're done. So q by d and x is nothing but a omega cos omega t. So you can get an alternating current using this. So as this plate oscillates in the middle, so you can actually create that SHM by putting springs here. That would have been even more fun. Then you will say the oscillations are small, so there is a force and yeah. But that would actually create a problem also because as you move it, there will be a force between these two charges also. Remember, force between the parallel plates, q square by 2a epsilon. We have to include that also. So that will give you one more force there. But luckily, if you see, q is also a linear function, isn't it? So your restoring force will still end up to be a linear function. So that would be a really good one. So yeah, that would still work. So that question would be something like this. Put a spring here, put a spring here. Just say k and k, and you say, if it is disturbed by a small displacement and release, find the current. And you could play around with that. You should try that as a homework. That would be fun. And that would be capacitors, current, electricity, SHM. Disturbed by small a. I'm just thinking it is solvable. So you guys try and tell me whether you're getting it or not. I just made it up. So I thought it is solvable. I'm not sure, but it looks like everything is a linear function. Should work out. Now, based on this, something similar, but let's say we have a shell and we have a shell and you have a point charge. You didn't give any charges to the shell, but you kept a point charge there. This radius is a. This distance is 2a. This is a, and this is 3a, concentric shells. We got a switch here. Some resistance R2 doesn't matter. This is S2, and we got one more resistance here with a switch here. This is S1. Okay, so initially the shells are neutral. There are two switches, and there's a point charge sitting exactly at 2A, and yeah, it's a thing. So the first question, find the charge distribution when both the switches are open. Then what you did, find the heat when S1 is closed. You closed S1, it will produce some heat. How much is that? And S2 is open. And then find heat when S1, S2 both are closed. So first you closed S1, you got some heat. Then you closed S2, then you got some heat. Take a minute. Think about only the charge distribution. This is a good one. I'll draw the charge distribution. Okay, let's see whether you got that much. Like, so both the switches are open. So I'll just remove these two. Right, I'll just remove these radiuses also. So this is your plus Q. So this plus Q here will induce some non-uniform charge distribution here, minus Q, and same thing here, non-uniform distribution plus Q. How much is small q? I don't know. And this plus Q will also induce a minus charge here, which will be again a non-uniform distribution whose value is minus Q. Why? Because if you take a Gaussian surface inside this conductor, the field inside the conductor is zero, flux is zero, therefore charge enclosed must be zero. So it should induce equal and opposite charge on the inner surface of the conductor. But it will be non-uniform because you see it's more closer to this thing. But once you go outside, again, you will get a uniform distribution. This time it will be plus Q. Shielding effect. Basically, the metal in the middle will not let any field lines outside. So the outside charges don't care what is happening inside. This will be plus Q. Actually, so if you take this plus Q and if you move around, this plus Q outside will remain same. That was a good mains level equation. If you move this charge inside, no matter what you do, this charge outside is unaffected. I hope you got this thing. This is the charge distribution. Right? So that small q and minus q, actually we cannot find. Yeah. Q cannot be found. So we are done with the first question. The second question is the main thing. So now if you close S1, S1 is this switch here. Can you find the charge distribution? Start with that. And then we'll try to find the heat. If you close S1, find the charge distribution. Wait, I'll do one thing. Wait, we can even do something better. The first question, right? Can you find the potential difference between the inner shell and the outer shell? Get this thing. This will help for the next question also. But this charge distribution, you don't know what is small q, right? But I want you to find the potential difference between the inner and the outer shell. Yeah, I mean, if the question was find the charge on the inner shell, it is zero. You cannot find the small q, but you know the total charge on the inner shell. can you find the potential difference between the inner shell and the outer shell for this distribution? And then we will close the switch one after another, and then we'll see. You can find the inner shell. That's doable. Outer shell is also doable, but we need to say something, and then it becomes suddenly doable. So think I'll give you a minute for this. It's a worthy question. Don't put yourself in pressure. Aram se think for a minute what to do and all. The time gets over, that is okay. No rush. I have to go fast because I want to teach you a lot different things, but take a minute, think. How do you find the potential on the inner shell? Okay, see, the inner one is doable. So this is the argument. See, what is the field inside that hollow shell? The field here is zero. Agreed? Why? Again, shielding effect. Because the inner one is a conductor, there will be no field lines inside, so that is zero. So that means if I can find the potential at the center, that will be the potential of the inner shell. So potential at the center is nothing but the potential of the inner shell. Because the field is zero, the entire thing must be equipotential. And why am I so obsessed about the center? Because of that small q and minus q. Only at the center, I can confidently say the potential due to these two is zero, isn't it? Even though the charge is non-uniform, even though the charge I don't know, but one thing I'm sure, the potential at the center will be zero. And how much is this? This will be k. I will still write it k minus q by a. So that guy is anyway gone. Plus, due to this charge will be k q by 2a. And due to the outer shell, k minus q plus q by 3a. So this guy is gone, this guy is gone. So this is kq by 2a. This is the potential due to the on the inner shell. Now, for the outer shell, you can't do this. For the outer shell, look at the problem. I want to find the potential here. So how will I find actually? If these charges are non-uniform, I can't assume the total charge is zero and I can't do this. Because you're getting the problem here, and look at this minus q also. This minus q also is non-uniform. You're getting it. Center was the lucky point, you know why? Because centers A, even though it is non-uniform, all these were equidistant, you didn't have a problem. You get the catch? So you cannot do this same logic for the outer shell part. We can do something else. What is the field outside? The field outside is only due to the plus q charge, which is k q by x square. This is only due to the outermost charges because everything else is shielded. This is only due to the outermost charge. So then I can do this thing. So V outer shell minus V infinity is equal to minus integral E dot dr. The limits will go from 3a to infinity. This guy would be kq by x square dx. V infinity is anyway 0. So the argument was this: whatever field is outside, that must be creating potential difference between the outer shell and infinity. So V outer will be, that would be kq by x, and the limits will go from infinity to 3a. So that's kq by 3a. Clear with this? So the difference will be kq by 6a. Are you clear? You cannot find the potential on the outermost shell using the regular formulas because it's all non-uniform. Then this is the argument there. The potential difference between the outermost surface and the infinity is created by the field due to the outermost outside surface, and we have finished it. Is this making sense? And this is not the first time we have done something like this in In Gauss law, if you remember, there was this question inside a cavity. We had to find the potential. ये question याद है? We needed to find the potential at this point B, and there is no direct way to find the potential at B. Then we did something similar. We argued the field inside is only due to the Q1 charge, and that must have created the potential difference between B and A. So the idea was same. So if you know the field in a region, but if you're not able to find this thing, this is something you can always play around. Clear with this? I got the potential difference with this thing. Now, if you close the switch S1, now what happens? Try, I'll give you a minute more. Now, if I'm closing the switch between the inner and the outer shell, maybe I'll just draw the new picture again. So find the heat produced. Now, just to give you a little idea there, you cannot use self-energy because the charges are non-uniform. You cannot use that capacitorial logic. Field is not uniform, so you're closing the switch. The resistor won't matter. So the first thing will be the charge distribution or whatever. Like, how do you find it? Think. You want a minute? आउटर शेल का आउटर सरफेस पर क्यू कैसा आया? Because the charge is conserved, because the outer shell is neutral, right, Devansh? Now the problem here is, see, the moment you close the switch, there will be some charges now. This will be some small q. I don't know how much is that. And if that is small q and this is plus q, on the inner surface, you should have minus of q plus q, right? And the outside, now remember, the total in and out is neutral. So if you add them up, this is 0, 0. So meaning, I'll just show you. If this is x, then q plus x minus q must be 0. So x must be capital Q. This would be the charge distribution where small q ka value I don't know. Clear with this? So again, the same story. So inner shell must be equal to the outer shell. So from there, I'll get the small q ka value. V inner is equal to V outer. And interestingly, if you observe, the outside charge still remained the same. So I can directly use this result kq by 3a for the outer shell. Nothing changed on the outside. And for the inner shell, same story. Again, we'll find at the center. So kq by small a. This charge is kq by 2a. And these two charges ka combination is k small q by 3a. This guy will be 4kq by 3a, and that would be minus kq by 6a. K goes off, a goes off. 3s are 2s are q by, I messed up something, I guess.
Minus 3 kq by 3.
Minus, yeah, minus double. Then that will be 2kq by 3a minus kq by 6a minus q by 4. There. These are the final charges when you close the switch. But this still didn't answer our question. We need to find the heat produced. So how do we do that? So the idea is this. So this is the situation after long time. Right? So Clear with this? Any doubts on this? Then, now here you can't use self-energy because the distributions are non-uniform. But tell me one thing, because there is a resistor, the moment you close the switch, do you think suddenly the charges will flow? It'll take time, isn't it? It's like an RC discharging circuit. So there is a time delay. So that means you will not become V is equal to V inner and V outer immediately. So let's say this is an intermediate stage. And let's say when you close the switch in this process, let small charge dq flow there. In time dt, let dq flow. Then we can say the small work done will be the charge dq into the potential difference, which is the V inner minus V outer. So every time the small charge dq goes from inside to outside, this much work is done, right? And the total work will be integral dq, and V inner is how much? V inner is these three. How much is that? 2kq by 3a minus kq by plus kq by 2a, and the outer is anyway constant, which is kq by 3a. So this is the potential difference as function of time, matlab a variable as function of small q. This is V inner minus V outer at time t. This is the potential difference, which is changing with q. And do you know the Q limits? What is initially value of Q? Q is the charge on this capacitor. Initially it was 0. Finally it was minus Q by 4. Making sense? So I'm finding that little work when it is going out. And what is all this work equal to? This must be equal to heat, isn't it? Every time the charge dq goes from inside to outside cell, so there's a small work done by the charges. So all this work done must be nothing but the heat produced. Are you clear with this? So you can integrate this. It's just this is anyway constant, and this is q power 1, so q square by dq. You'll get it. Now what happens if you close S2 also? Now this is an easy one. So once you got this distribution, so once you close the switch, what do you notice? So once you close the switch, look at this thing, the field lines which are there outside. So this is the field there. Now suddenly the field becomes 0 because this Q will become 0. Make sense? Why will that be 0? Again, same argument. See, infinity mein potential is 0. This is grounded, so this is also 0. So there cannot be any field between infinity to the shell, isn't it? So there's no need to calculate. You can just argue with that. Since when you grounded the outer shell, that was the reason, you couldn't use that argument in this question. Huh? In this question, you cannot say the argument, okay, this is 0 and this is 0, so field will be 0. Not necessary, because there is a shell in the middle. You can do this only for the outer shell. For the outermost shell, the next shell is infinity, and if there is no potential difference, there should not be any field lines between them. So, matlab, all this field vanished. So what is the heat? Is nothing but the self energy of the outer shell. What about the inside? The inside one does not even know what is there outside. They both are separated. Getting it? Completely shielded. The inner and the outer will behave like two independent systems. There is no interaction between them. Self energy, how much is that? Q square, K Q square by, what is the Selka formula? 2R, and R is nothing but 3A. Clear with this? So this is the heat when S2 is closed. The S2 part is the easiest one. So if at all they ask you something like this, you'll get question 1 and question 2. 2 will be easy to solve, 1 might be difficult to figure it out. Because if you look at this question, right, to do this part when S2 is closed, I don't even care what is the charge inside, isn't it? You need not find what is the charge inside. You need not find the potential. You need to do nothing. Matlab, you can just argue the outside charge is gone and that's the self energy and you're done. So when you see a question, always think about this. Generally, this is something I noticed. Advanced, whenever the paragraphs become very deadly, right? One question will be like a joke. You can handle it. One question will be like really gone. So maybe you can figure out one. Clear with this? So that's a pretty good one based on Gauss law. You can see heat and all that stuff. So then let's see a few questions on circuits. And if you're going through the nodes, right, most of the circuits we have done in capacitors, we didn't do in current because they're the same thing that, axial symmetry, bisector symmetry, cube symmetry. There were a lot of symmetries that are taught. So make sure to go through that. It's all there in the capacitor nodes. This is a standard one. We have done it multiple times. So yeah. Just find the current in this branch. All batteries are V. You should check out in the notes. There is 2 questions like this. All batteries are V, all resistors are R. Find the current in that branch. This is more like a puzzle. You know how to do, you see this question, you'll get a smile. You don't know how to do, you'll see this question, you'll feel like, what the hell? So if you've seen this before, it feels like nice. If you have not seen this before, it will feel like, what the hell is this? Won't Q inside of the change to match the zero potential? Why? The inside charge does not know who is outside.
Sir, but potential on the sphere inside should also be zero, right?
Right,
Because
my
Q is
mistake.
inside.
वो actually S1 open S2 close था वो. सही है. S1 open S2 close था वो. Because if you close that also, inside also will be zero. Then we'll have problems. Then this field also will vanish, right? And things will start getting. Then Q भी निकालना पड़ेगा अलग से. That would be a different question. It won't be this easy. You have to again do something. Did you get this? Yeah, the previous one, S1 was open and S2 was closed. What is the catch in these kind of questions? You have to find a loop such that you have only this one resistor and remaining all must be batteries. So it's like you have to find a path. This whole thing can be treated as one resistor. How much? R by 2. So this is 5R by 2 chunk. So find a path. You go like this. Make sure you should not touch another resistor, okay? You should not touch a second resistor. You can go through only batteries. Why is that? Imagine when you write Kirchhoff's law, what do you write? V minus IR, right? So if you go through another resistor, I don't know the current in that resistor. But as long as I pass through a battery, it doesn't matter how much current flows through it. There, can you see? So go like this, go like this, go like this, go like this. See, I didn't touch a second resistor. And then you're back again. So you can count the number of batteries facing each other opposite and you're done. You'll solve it. Clear with this? Easy one, not difficult, but like I said, if you have not seen this before, you'll feel like, oh, what? So there was one more like that, which we did. I think it was the same thing, yeah? No. Same thing, but here they asked for 2 currents. This is I1 and this is I2. Can you just find the path for I1? Just find it. I'll give you 20 seconds. Then you know how to do. This is I2. It is the same circuit. These are called maze circuits. It's like a maze. If you ever read this Hindu newspaper, में उसमें आता है ना, like help the rat catch the cheese or something like that. Did you guys found I1 ka root? So start like this. Can go like this. There. Got it? So that once you get this, you can figure it out. This is another beautiful question. We have done in the class notes, but it's a worthy question. Let's see how many of you remember this. So we have a circuit like this. This is 1 ampere going out, 1 ampere coming in, 1 ampere going out, 1 ampere coming in, 1 ampere going out, 1 ampere in, out, in. Bus, this much we know. You need to find what is the current in the branch AB. All resistors are, doesn't matter. So you know only current in these branches. 4 are coming in, 4 are going out. So yeah, nodal analysis still valid. Now junction law is still valid. Using this data, find the current in the branch AB. So that is one thing. Again, advanced merit, they will not expect you to literally put equations and solve. They'll mostly try to play around with symmetries. So like the exam is not to just see how good you can do calculations. It is about like, can you think? Can you figure out something? So right now, if you already know, like, I'll give you a minute. You should have gone through the notes. You would have seen this. I'm telling you, this is what will happen. Exam right? Forget about in that entire paper, right? There'll be at least 50-60% questions you can handle if you're thorough with your notes. After the exam gets over, then you'll realize, shit, this was there in the notes. So, and every year it happens. I think even last year, 2 questions came directly from the notes. Literally, matlab, almost the numbers were, I won't say numbers are same, but heat transfer. We are going to do it again, the revision, but this was a question. N plates. This is not the first time, and it's not like I'm predicting questions or something. When you do so much, right, something or other will keep popping up. Electrostatics, we did dipole forces. These things came in on matrix matching. It comes. It is not because I'm predicting something. When you do so many models, something or other will pop up. The concepts are limited. How much they can play around? Yeah. What is the answer? 29 for this. So I'm telling you, if you are not done with the notes, that is the first place where you should spend some time. You still have time, right? It is worth spending time, and then you can do more material and extend. Anyway, you're attending the session, so that takes care of few more models. So how do we start this question? So the idea is this: let all resistors be R. Okay. Anyway, it doesn't matter. So let R be 1. So start from the center. Let this be 0. If this is 0, from junction law, this must be how much? Current always flows from higher to lower potential. This is +1. If that is +1, this is -1. This is +1, right? And then so that is +1, and wait, no, this is -1. Now, if this is +1 and this is -1, the potential difference is 2. And the potential difference is 2, then this current will be 2 ampere and this current will be 2 ampere, right? Similarly, this current will be 2 ampere. Making sense? And this current was 1 ampere. So 2 ampere is coming from here, 2 ampere is coming from here, and 1 ampere is coming from here. That means in this branch, 5 ampere current is going. And if this is 5 ampere and this is -1 volt, then this must be -6. V is equal to IR. The potential difference is -6. If that is -6, you can use the same argument here. Here, the 5 ampere current is coming. This is +6. This is +6. If that is +6, that means this is 12 ampere current and this is 12 ampere current. So 12, 12, and 5 is coming. So the current in the branch IAB is 29. Clear what we did? Junction law. You just kept on arguing like, okay, if this is 0, this must be -1, this is +1, this is +1. And then we found the current in those branches, and then we just kept on adding. Yeah, once I explain, it looks easy. First time it doesn't click. I'm not saying they're going to ask the same thing, but you will see something like this, some part of this. So that is the whole point. You'll not get the exact same questions. But the idea is important. When you see a junction law, you can figure out like this. Clear with this? So there was one question in the class notes, which we did something. Hope you guys remember this. So this is voltage V, let's say 1 volt, 1 volt, 1 volt, 1 volt, 1 ohm, 1 ohm, all resistors are 1 ohm. All right, so this was A and this was B. Find VA minus VB. You can add one more resistor here also. Yeah. Wait, I'll do one more thing. Wait. Add few more batteries here also. Yeah, this was the question. This is also 1 volt, 1 volt, 1 volt, and 1 volt. Better. Yeah. There's nothing in series, nothing in parallel. So circuits, right? There are two ways to solve. One is the junction law and one is the Kirchhoff's junction law and Kirchhoff's loop law. Between these two, Kirchhoff's junction law is more preferable. It is faster. It will always give you one equation less, saves you time, and kind of safer if you ask me. The Kirchhoff's loop law is good, when you're playing something like this maze circuits and all, when you literally have to travel around. Or when you have an inductor, capacitor, resistor, sub mix ho gaya, generally the loop law is good. So how do we start this thing? So in this primarily first thing is the junction law. So if you go back to the notes and check it out, right, we wrote a full process how to solve a circuit. So the first thing was assume a point with zero potential, because if the circuit does not care what is the potential. So let's start with this zero. Once you assume zero, try to find the potential at the other nodes. Luckily, if this is zero, this must be 1, this must be 2, this must be 3, and this must be 4. If this is 0, let this be x. So wherever you don't know, start with a variable, and this will be x plus 1. So this must be x plus 2, and this must be x plus 3, and this must be x plus 4. So indirectly, if I can find x, my job is done. So this is the step 1 in the junction law. Step 1, this is the starting process. Assume any point as 0. From there, try to find the potential of the other nodes. Wherever you can't find, assume a variable and just figure it out. So here, the only variable in this whole circuit is x. If I get x, I can actually find whatever you want. I can find the current in this branch. I can find voltage in that branch, anything you want. How do you find x now here? Remember here, there is no current ka term anywhere here. You will take the rightmost loop and then what? कर लेना actually इतना confident है तो कर लो एक step में. Loop law, what loop law? Do you know what is the current in this branch? Do you know what is the current in this branch? Then what loop law will you apply? The I1, I2 will be different. So there's nothing called line law, but idea ye hai. See, normally what is the junction law? The current entering a node must be 0, isn't it? If you take any one node, the total current that enters a node must be equal to the current leaving the node. Do you agree with that? That's your junction law. But here there are so many junctions, you can do something even better. What if I draw a line like this? Can I argue this? All the current that is crossing this line must be 0. And not only for this circuit, you take any circuit, you can actually use this. So for example, if you take this weird circuit, right, if you just draw a random line like this, you can argue every current that crosses this line must be 0, the sum. Any idea why? Because think about it, Kirchhoff's loop law, if you start from any loop and if you come back, all these loops, the current must be, in a net loop must be 0, isn't it? If you take a round trip and you come back to the same point, the current must be crossing and must be coming back inside. Is that making sense? So it doesn't matter which loop you take, the net current will be 0 there. So this is valid for any circuit here, okay? So I can do for this, great. So this current and this current, this current, this current, this. So we have to find the current. What is the current? Potential difference by resistance. So what is this current? The potential difference will be x plus 4 minus 4 by 1. What is this current? X plus 3 minus 4 by 1. X plus 3 minus 3 by 1. X plus 2 minus 3 by 1. So x plus 2 minus 3 by resistance. X plus 2 minus 2 by 1, x plus 1 by 2 minus 1, x plus 1 minus 1 by 1 plus x minus 1 by 1 plus x minus 0 by 1 must be 0. The total current crossing the green line must be 0. Clear with this? If it is not 0, what happens? That's what happens, go revise the notes. This is from the class notes. If you guys are shaking your head, oh, what is this? That means you're not bothered to revise the notes. Right? So think about this. If the net current in this line is not 0, meaning what? Current is flowing in one direction. That means the current is not returning back to the batteries, isn't it? So eventually what would have happened? Think about this. If the current is just flowing in one direction, won't this point become negative charge and this becomes positive charged? Is that making sense? That means whatever current is entering the line must be crossing back into the line somewhere. We don't know where. It is simply the charge conservation. So you can apply the nodal analysis not only for one node, but you can apply for 10 nodes together. Are you clear with this? Each branch is a resistor. So this is B, this is A. Find RAB. So R, everything is R. You read right. Let's see how to do this. Anyone remember what is this? There is an axial symmetry and a bisector symmetry. I don't remember the answer. 13R by 7. 13R by 7. Okay. Could be. So how do we handle this? So first thing, there are two symmetries here. If you see, the left and right are equal. So if the two terminals of a battery are on either side of the line, we call this thing axial symmetry. And what does axial symmetry do? This entire line becomes equipotential, because see, for every point is a midpoint of AB. Every point is a midpoint of AB. So all these points will have a potential of V by 2. So that's an equipotential. So any resistor or capacitor between these 2 points, that means in this question, if I had given resistor here like this, I could have removed them. They don't make sense because there's an equipotential, you can remove them. So it's an equipotential thing. Other than that, if you see, the line joining through A and B is also symmetry. This is called, no, wait, I wrote wrong. That is your perpendicular bisector symmetry. So bisector there. This is your axial symmetry. So in an axial symmetry, if you see the either side, see, don't read it as up and down, right? If you line is passing through A and B, because A and B can be anything, the up and the bottom are identical. That means you can fold the circuit. So that means the upper one and the bottom one are parallel, isn't it? So the circuit can be folded like a waffle. Did you ever see when they make a waffle, how they make it? So they have this round thing. They put, let's say you ordered only one waffle. They will put all the batter here on one side. And after it is done, they'll simply fold the waffle. That's why you got a quarter circle waffle, right? So something like that, you can fold this. And when you fold this, what will happen? Resistors, when they fall on themselves, when they're in parallel, resistance becomes R by 2. So this is how the circuit would look. This is B and this is A, right? So you'll get an half circuit like this. And this each one becomes R by 2, R by 2, R by 2, and everything becomes R by 2 there. And one more thing about this bisector symmetry, they become equipotential, and next thing, all nodes can be opened up. All nodes along the line can be opened up. Again, how can I do that? I mean, look at this node. Again, the argument is this. By symmetry, if this current is I1, this current is I1. If this current is I2, this current is I2. Do you agree? Because if you look at the line here, see, this current I is entering, this current I is leaving. So whatever happens on this side, the same thing should happen here in the reverse. So if the current entering and the current leaving from the node, so I1 is coming and going like this, I2 is coming and going like this, you can assume like that. And that means that node is actually useless. So your new circuit becomes so you can just remove this node in the middle. So axial symmetry does two things. It creates equipotential and you can open up all the nodes like this. So it opens up like this. Clear? I think then it is done. It's doable. So R, that is R by 4. This is R. That will be R by 2, 2R, again R, and this is R, and this is R. This is R, and this is R. So your whole circuit will look like resistor. That would be 3R, R by 4. Wait, no, everything became R by 2, na? R by 2, R by 2, R by 2. This is R by 8. So R by 8, R by 2, R by 2, 3R by 2. Nee, wait, why R by 8? Sorry, it's they're in series. Shit. That's 2R. Clear with this? And then you can just check it out the calculation. But I hope you got the idea there. So once you remove that branch, it becomes quite easy to handle. Clear? So axial symmetry, bisector symmetry. You use both of them. In case you have forgot or you don't remember, please go through this, because these are the things which I took a full class to explain. I can't do justice in 10 minutes. So here we wrote a full story there. See, symmetrical circuits, perpendicular bisector symmetry, either line is symmetry. nodes can be removed, element can be removed. So then I gave an examples, which node can be removed. Then there, it's the same question which I gave. We didn't solve it though. Then I said axial symmetry. Then I gave an example. So we have done something similar for capacitors, right? You should definitely go and check it out. Let's do this. Previous one, diagonal symmetry. God, when you say symmetry, about A and B, there should be symmetry, right? How will you draw diagonal symmetry for that?
So, but in general, for the general structure.
General क्या? Diagonal symmetry कब आता है? बताओ. When this, na? Let's say R, 2R, 2R. ये Wheatstone नहीं है ना? Then इसका argument क्या आता? We will say current in this and current in this is same. So then we will say if this is V, this is X, this is 0, so this should be V minus X. Na? So the potential difference in this and potential difference in this must be same. That's your diagonal symmetry. It's really not that powerful, but it will just eliminate you one equation there. I'll show you one.
And the other one.
Where?
In the question, the line law.
This one.
Also the one with the multiple batteries.
This one.
Yes. Yes, for like figuring out X1, X2.
I don't know. Maybe you can. You try and tell me if you got the answer. You know the answer already. You try and you tell me if you got it. I didn't think about it. Because when you have 10 batteries, right? Kabhi dekho, observe karke dekho. Symmetry ka discussion comes only when there's only resistors. You have 10 batteries, 8 batteries. Generally, first thing, it never hits me that I have to use symmetry. Generally, that is what I observed. Whenever they play with symmetrical things, they'll just give you a bunch of resistors and last find the R equivalent. But yeah, maybe give it a try and see. Usme na, if the batteries maybe are in the reverse, so you could have argued maybe. The upper one are going in one direction, bottom is going in another direction. Then maybe you could have said something like that. Because there it doesn't look symmetrical. If you draw a line like this, it is going this way. If it is going this way, then it would have been diagonal symmetry. How do we handle this, everyone? Just open the circuit and show me how it looks. Then you are done. Matlab, if you can draw that series parallel thing, you're done. In this, you have both axial symmetry and bisector symmetry. So first thing, you can start from here. You can clearly see this is an axial symmetry here. You can open this. And up and down are in parallel. You can fold it also. Then your circuit would be one, two, three, four horizontally. 1, 2, 3, and 1, 2, 3, and you're connecting them. Advanced exam with them rough work they give you, drawing and all, and you won't be so comfortable also. They'll not give you a big bench or something, right? How much place you have in front of the computer? Do you have enough place to keep all the stuff, or it's little stuck? This is the thing. Did I miss something here? Na, sab ho gaya na? Perfect. This can be removed here. Perfect. Now, when you fold them, observe this. when you fold, this R will fall on this R, this R by 2 will fall on this R by 2, this R by 2 will fall on this R by 2, but the middle resistors, these things are only single, isn't it? So they will not get affected, but everyone else will become half. So the middle ones, I will be R by 2, R by 4, R by 4, R by 2. These things will not change. Perfect, but the rest will become half. So I'll just leave it like this. Rest becomes half. Maybe I can write few of them. So this is R by 2, R by 2, R by 2. Perfect. And then what? This thing, if you see carefully, right? You can just open it up. This was A and this was B. So this is that bottom ones. R by 2, R by 4, R by 4, R by 2. This is R, R and R. That thing can be done into one. Calculate करना पड़ेगा, I guess. R by 4, R by 4, R by 2, R by 2, R by 2, R by 4, and that's R by 8. So this full chunk here will be R by 8. And if you go top now, this is 1. This is that green ones. R by 2, R by 2, R by 2. And this middle one, the black spot will come here. This is 1. And the other one comes here. These are the two black spots. And in the middle, you have that R by 8. There. These are all the resistors there. And can you see something here? There is again, there is a symmetry, right? You can fold it again because this R by 4 and R by 4 will become again R by 2. So the top 3 R by 2 and the bottom also all 3 are R by 2. Now again, it's a symmetry. Again, you can fold it. If you can fold this again, now this will become so this guy will still remain R by 8, but rest of them will become again half. So R by 4, R by 4, R by 4. How much was that black thing? That was R by 2, R by 4, R by, this was R by 4 and R by 4. So that would be again R by 8 and R by 8. It is doable right now. Okay, na series parallel, you can solve. So axial symmetry, bisector symmetry. This is how you play around. Got the idea there? So if at all they ask you circuits, they will expect you to know the symmetries and figure out. This is more of a thinking. देखा कुछ calculations कुछ नहीं है. Answer is 13R by 20. You can verify later on your own. So, but the idea is clear, everyone. Perfect. Next one. Yashil.
Can you just go to the previous page?
Yeah.
So here in the mark dots, the dots here, about that, can we just separate those points into two halves, like one trapezium and the other one in the M shape? Can we do
Why?
that? Because it's symmetrical, right? So we can we
About
just do that?
symmetrical about what?
No, the vertical axis, so we can just.
This is symmetrical. ऐसा बोल रहे हो?
तो फिर वो
Okay, then
ट्रेपेजियम जैसा है ऊपर वाला, नीचे एक एम शेप जैसा.
नहीं, you can't do anything like that. I don't know what you're saying. How will you split it out? Diagram draw करके भेजो. How you want to split it? We'll see. You draw lines, split them, and send me once. मैं देखता हूँ कैसा है. Do you guys remember this? Infinite grid. So there's an infinite branches, and each segment is R. But we will change it a bit. So it's just going ever-ending circuit here. It's an infinite grid. This is point A, the midpoint, and this is B. if you remember the question, we did between these two. Yeah, we're not doing that. We are doing between these 2 points. Find RAB. Meaning on the top, it is not infinity. At the bottom, this full thing is infinity. This side, infinity, infinity, infinity. The upper side, you can see the top surface. Find RAB. The class notes, what we did, that was a big grid, and I gave you 2 points in the middle, A and B. In case you forgot the idea there, how do we do for these infinite grids? Didn't do that. I think capacitors में किया हमने. Again, go back to when you want to check for circuits, check in capacitors only. We did everything there only. Did I do that? Here. So यहाँ पे idea, right? We are using something called principle of superposition. So the idea was this. Listen again. So when you put a battery between A and B, current I goes from A and comes from B, isn't it? So idea here is, what if I send only current through A? So here A is one terminal, infinity is second terminal. So current will enter from A, and because of symmetry, it will split, Q by 4, Q by 4, Q by 4, Q by 4 equally in all directions, and it will spread to infinity. Similarly, what if I take charge from B only? Matlab, I'm forgetting about A. So here the positive terminal is infinity and the negative terminal is the point B. Again, by symmetry, Q by 4, Q by 4, Q by 4 will come from in all directions. Now, if I superpose the circuits, if I combine these two, so whenever you send charge through A, you get Q by 4 in the middle branch. Whenever I pull charge Q from the B, you get one more Q by 4 from the middle branch. This is called principle of superposition. If event 1 creates effect 1 and event 2 creates effect 2, when you have event 1 plus 2, you have effect 1 plus 2. And to give a simple example, let's say you have a block of mass M, and if you apply a force F1 bar and you get acceleration A1 bar, on the same block, if you apply force F2 bar and if you get acceleration A2 bar, then when you apply F1 plus F2 bar, you get acceleration A1 plus A2 bar. This is valid for, it works. But the only thing, the event should be independent of each other. If you have two independent events, this will always work. This is called principle of superposition. Now see what happened then. When you combined both of them together, so when you're sending Q through A, you got Q by 4. When you're pulling B, you're getting Q by 4. That means when I do both together, I get Q by 2 in the middle. And then you're done. So VA minus VB is equal to Q by 2C, and C equivalent is nothing but charge by potential difference, so 2C. So this infinite grid capacitance was 2C. This is how you handle infinite grids. And then if you remember, we did an hexagon also. So there are variations of it. Please make sure to go through the notes. Idea was the same. So here पे भी same logic use किया हमने. Q by 3, Q by 3, Q by 3, and we played the same game. So that was principle of superposition. So we have to do something here. Infinite grids, there is no way you can use it. Kirchhoff's law, Ohm's law, कुछ नहीं होता है, मतलब junction law and all that. Principle of superposition is the only way. Yeah, Ohm's law तो है ही, but how do we handle this? This is an infinite grid with I mixed up a symmetry also. I'm not teaching you cube symmetries, so please make sure to go and revise in the notes. In symmetries, right, we have varieties. We have infinite grids. And there are other infinite grids also I taught. You should check it out. Right? We have axial symmetry, bisector symmetry, diagonal symmetry. Right? We have cube symmetry. We have infinite grids. So we have around 4 to 5 varieties there, and you can get a combination of them. So what's the idea there? See, the story is always the same. Assume only A is there. If only A is there, meaning the other terminal is at infinity. So if I send current through A, it will split I by 2, it will split I by 2. And you can clearly see there is a line of symmetry here, isn't it? So about this point A, the left and right are looking identical. Whatever happens on the right, the same thing will happen on the left. That means this point and this point are equipotential. This point and this point are equipotential, and so on. because the left and right are same. So if I give them names, I'll call this 1 and 1. I'll call this 2 and 2. I can call this 3 and 3. So all these resistors can be removed. Again, I'm sending only current through A. That means your new circuit will look something of this sort. So this current is coming I, and this is I by 2. And again, can you notice something here? If you see from here, again, I didn't draw it properly. If you draw a line passing, shit, why is this so bad? Like this. Can you see even that will be symmetrical again? So this half and this half are identical, right? About this point, if you see, this is a big infinite grid, isn't it? If you draw a line like this 45 degrees, that will be symmetrical. So that means current again here will split I by 4 and I by 4. Now after that, what happens, I have no idea. But till here, we can figure it out. Is that clear, everyone? So whenever you send current through this point A, I by 2 will go to the left side, and then again it will split into I by 4 and I by 4. Clear with this? Same way, when you take current from B, I can do the same argument. You'll get I by 4 and I by 4. Now, if I do both at the same time, so when I give current I here, this branch is I by 2. And remember, this branch used to be I by 4. When I pull current from I from here, this is also pulling in. This is pulling I by 2. And this branch is pulling I by 4. Make sense? And now if you write the resistance between A and B, so we have an half resistor here, R by 2, because that is half the branch. Another half resistance, R by 2, and then comes B. And if you look at the current in both of them, the current here will be I by 2 plus I by 4, 3I by 4, and 3I by 4. Then we know VA minus VB is equal to 3I by 4 into R. 3I by 4 into R. And we know R equivalent is nothing but what is R equivalent? If you apply a battery, VA minus VB, and the current through the battery is high, so that would come out to be 3R by 4. So that entire grid resistance is 3R by 4. Are you clear with this? I used two symmetries here, the infinite grid logic, that is principle of superposition, and then again an axial symmetry. So you removed all these resistors in the middle. And then we said, this entire half is equal. So 45, 45. So this part and this part are equal. So again, it will split I by 4, I by 4. Clear with this? You should check out that principle of superposition thing there. All clear with this? Similar one, again, if you remember this, take a break. Come back in 5 minutes. We'll continue from here. In the meantime, I'll just put up a question here. Come back by 7:30. Sure, let's do this thing. So there, I created another big infinite grid, all made of triangles. So this thing is just triangles, triangles, triangles everywhere. Find RAB. This is not the actual question. Principal superposition. You see in a big infinite grid, principal superposition is the only technique that at least we know. So how do we do this? Same story. Let the current only flow through I, and this would have been I by 3, I by 6, I by 6, I by 6. And if you pull current I from here, that also would have been I by 6. So that would have been I by 3, right? So VA minus VB would be I by 3 into R. So resistance between A and B would have been VA minus VB by I, which is R by 3. Easy? So when you send current I, it'll go I by 6 in all directions, isn't it? Because there are 6 branches here, I by 6, I by 6, I by 6, I by 6, I by 6. Similarly, when you pull current from B, you'll get again I by 6. So in the branch AB, you'll get I by 3. Okay with this? That was an easy one. Now, so infinite grids, right? They look scary, but they're manageable if they give only that much. But now let's say you remove this capacitor, one resistor between them. Let me call this point also as C. And then you decided to remove BC. There I'm putting a dotted line. Now find RAB. This thing symmetry is gone. Don't think in terms of this problem. Matlab, you know, if you put a resistor there, it becomes a symmetrical. But now it is not there. So how do I handle? So concept is not this problem. Meaning you can do what I'm going to teach you now for this. You can use it for any other logic. Just by putting one resistor, it becomes symmetrical. So how do we start? Now, the idea was this. Just now we calculated something, isn't it? So if you take this full circuit, the resistance between A and B is R by 3, right? So can I say like this? If I take the whole circuit and I will call this point C. So between A and B, this whole circuit, what you got was R by 3. And between B and C is also it's R by 3, right? And I'll just put only 3 points then. I'll take A, B, and C, right? And I can treat them like this. It is symmetrical, isn't it? So there is a lot of bunch of things here, bunch of things here, and bunch of things here. So that whole infinity, this entire grid here, I can replace with one resistor. How much is that? I don't know. Getting it? So I can replace this whole thing with a resistor called X. Again, because it is symmetrical, this is also X. This is also X. So this is A, this is B, and this is C. You're getting the argument? From A to B, I don't know whatever is this chunk. I can club this into one. Between B and C, this entire chunk I can club into one. Between A and C, this entire chunk I can club into one. And again, remember A, B, C, all three are there. I didn't remove anything now. Now, because there's a symmetry, I can say, I don't know what is the value, but they must be equal. And I'll take it as X and X and X. So now, if you take between RAB from this logic, X and X are in series, and that is X, so that is 2X by 3. But we already proved RAB is nothing but RA3. That means X is equal to R by 2. Are you clear with this? That means this complete infinite grid can be replaced by 3 resistors of R by 2 between A, B, C. And this would have looked identical. Is that making sense? So far clear? And now comes the question. Now, what did you say? You removed the resistor between B and C. So this was A and this was B. Now the problem is, remember you derived R by 2 when this system was symmetry. So this is how I will argue now. I will say this resistor which you removed, I will add a resistor R, and I will also add a resistor called negative R, so negative resistance. Because mathematically, that point should have how much resistance? What is the resistance of an open junction? Infinity. So 1 by R equivalent must be 1 by R plus 1 by minus R. That will be 0. So R is infinity, isn't it? So we can use something called a negative resistance. Now, physically it doesn't make any sense, but mathematically it's fine. It works. So we introduce a negative resistance to make it a symmetrical circuit. So that is the main idea there, right? So that 1 by R equivalent will be 1 by R plus 1 by minus R, and this would be 0, and you look at R equivalent is infinity. So this is an open circuit. So the idea here is whenever you have a one branch missing and you can make it symmetrical, you can introduce a negative resistance. Yeah, it doesn't physically make sense, but mathematics doesn't care what you're talking about. Yeah, it works like this. So now your question becomes, so this is A, this is B, this is your R, this is your R, and this is your R. And there is also now your negative resistance. Sorry, not R, R by 2, R by 2, R by 2. And your negative resistance minus R. Clear with this? Just now we proved now this whole grid can be replaced with R by 2s. So simply you have added one negative resistance to BC junction. Done. You can use series parallel. It works. Negative resistance will just work like series parallel. So resistance across RAC will be, you can finish off from here. So just take it as a minus sign and solve. I think you'll get 3R by 8. I remember the answer. Are you clear with the idea there? Because of that one branch, the symmetry was lost. So by introducing that one branch and putting a negative resistance will create your symmetry back. And just now we proved this whole circuit is nothing but 3 resistors, X, X, and X. So if that branch was missing, I just need to put a negative resistor and it works. Clear with this idea? That's a concept of negative resistance. Mathematically, it makes sense. Physically, there is no meaning to it. Just to solve a problem. Clear with this? That is one. That's a little bit about all the circuits. I kept them together. So do make sure to go through them. This is another good one. It's not a tough one, but it's a good one. Again, we will see something like this in heat transfer again. So we have a solid sphere with a cavity. So here resistivity rho is equal to rho naught x. The inner radius is A, outer radius is 2A. So we have a battery here, which is grounded. This is voltage V, and this is grounded to the ground. So matlab, the inner surface ka voltage is V, and the outer surface ka voltage is 0. This is the conductivity. So current is flowing from inside to outside. So this whole voltage is V. So current is flowing radially. Find R equivalent. Find the current density as function of x. Find the electric field as function of x. Find the heat produced per second per unit volume is proportional to x power n. Find n. Find voltage as function of x. The outer layer is grounded with 0. So the potential will go from V to 0 as you go outside. Find the voltage as function of x. It's a solid sphere with a cavity. So the flow is radial. Your resistivity is rho naught x. So as you go outside, it is becoming more and more resistance. I can even ask you something better. And find charge per unit volume. As function of x. I'll talk about more about this in the next class also, but currently we can still try. So there'll be some charge actually induced in this. Matlab, when the current is flowing, something happens and there'll be some charge all over this conductor. And remember, in Gauss law, you studied this thing. There'll be no charge inside a conductor for static charge distributions. Did you also study this in Gauss law? Remember, field inside a conductor is 0. But when a current is flowing through circuit, J is equal to sigma E, the field is not 0. So be careful. That statement field is 0 inside a conductor is valid for static charge distributions. When you have a battery, the charges are continuously being pushed. It is a kind of a non-steady state. The battery is always trying to bring the charges to equilibrium, but that is not happening. So be careful with that. Explain the question. We have a solid sphere with a cavity. Inner radius is A, outer radius is 2A. There is a battery inside, voltage V. Maybe the picture was not clear. So you connected a battery here and you grounded inside. So this whole surface ka voltage is V. Outside is grounded to 0. So the current will flow from inside to outside like this. Clear? So find R equivalent, find the J of x. J is the current density, current per unit area. E is the electric field. Heat per second per unit volume is proportional to x power n. Find the voltage as function of x. Find the charge per unit volume as function of x. So something happens and you start getting charges there. So you need to figure out why you get charges. But let's start from the resistance R equivalent. That you can find. That is the easiest one. This would be a pretty good advanced paragraph questions. Like, yeah. How to find R equivalent? At a distance x, take a thin shell. Dx. So the small resistance dr will be rho L by area. So rho is rho naught x. L is the length along the current flow. Here the current is flowing radially dx by A. Area is the cross-sectional area perpendicular to the current flow, which is 4 pi x square. That would be rho naught by 4 pi dx by x. So you want the full resistance R equivalent, integrated this, you'll end up with rho naught by 5 ln 2. Clear with this? Once you got the R equivalent, current will be nothing but potential difference by R equivalent. What is the current density? Current by area. Current is anyway constant, area is 4 pi x square. But what is J? J is nothing but sigma into E. But what is sigma? Sigma is nothing but 1 by rho, which is rho naught x into E. So there you get E also as function of x. I rho naught by 4 pi x. So they can ask these questions as integers also. E is proportional to 1 by, x power n, find n and all that stuff. What about the heat produced? Now he's asking heat produced per second per unit volume, meaning in a small region, okay? You're not asking for the entire thing, right? Again, you're asking as a function of x. So that means for a small region at a distance x, you want to find the heat produced. What is the heat produced? I square dr. So this is the resistance of that small region x. That's the total heat produced per second by the volume of that particular region is 4 pi x square dx. Is that making sense? So if you take a thin shell of thickness dx, that resistance of that thin shell is this much, drx. And luckily here, all are in series, so current flow is constant. So I square is anyway constant. drx is this guy, so which is rho naught dx by 4 pi x. This is 4 pi x square dx. So that is the reason I gave per unit volume, so that dx term will cancel off. You end up with I square rho naught by 16 pi square x cube. So that it's proportional to 1 by x cube. Clear with this? That's your heat per second per unit volume. Question is still not over. How do you find the voltage and the charge? Find the voltage, charge, we will talk about it. Voltage is a good one. The same question, how I'll ask you in heat transfer. I will say there's a conductor here. The inside temperature is 2 T naught. The outside temperature is T naught. And I will say the conductivity K is equal to K naught X. Find the thermal resistance, find the heat flowing per second, find the temperature as a function of X. Idea is still the same. Getting it? I can also play like this. Let the voltage be 2V, V, and there is a dielectric slab in the middle, K. The dielectric constant is equal to K naught X. Find the equivalent capacitance, find the, the voltage as a function of X. I can play around like that. I hope you're getting the idea there. So there, you can keep doing all that stuff. So the ideas are the same. How do you find the voltage as function of X? Two ways you can handle. One is you can find all this resistance till here, which can be done. Limits will change from A to X. And then you can say potential difference is I into R, isn't it? That is one faster way. Or you can actually do this also. So when you take this thin shell, the current flowing is I. So I will say dV, the potential difference across the thin shell, is equal to minus I into dr. Why minus? Because the potential difference drops. So dV, current I is constant, and this will be rho naught x by rho naught by 4 pi dx by x. Integrate. The limits will go from A to X. Here the voltage is V, and this will be V of X. So V of X minus V is equal to minus I rho naught by 4 pi ln X by A. That's your voltage as function of X. I ka value, you can take it and substitute here. Clear with this? Got this? What about this charge ka story? Like, where the hell are you getting charge from? This question, right? If you have gone through the notes, you would have noticed a question like this. It was very easy to solve, but there was a very interesting idea there. ये question था, याद है किसी को? you have two composite wires of resistivity ρ1 and ρ2. And when the current I was flowing here, something happened and there is a charge got stuck at the interface. Think of it like this. You have a beautiful highway, right? And let's say suddenly the road has become bad. So you have a beautiful highway and the road became a kacha road here. So when the traffic is going, there will be a lot of big traffic jam at this junction, isn't it? The charges will start accumulating there. So even though it is a conductor, you'll still have charges there because you mess up the resistivity. And this was the idea there. Then we said, okay, we have taken a Gaussian surface and we found the field using J is equal to sigma E. And then we said the total flux, because the field is different, now there'll be charge enclosed here because there's a flux. And look at the idea there. Meaning, once you know what is happening, it is just 2 to 3 steps. Clear with this? So the same thing now I can do here. So we will do the same argument there. We will say, so we will say here the field is E, and here we will say the field is E plus dE. Because of the difference in field, the flux in that small region will be E plus dE into area minus E into area, which is dE into area. Right? And this is nothing but the charge enclosed by epsilon, right? And if you multiply dE by dr, and this will be A into the dx and dx. That's Q by epsilon. This becomes the volume term. So dE by dx into epsilon will be Q by volume. That's your charge per unit volume. And what is E? E we already calculated. E was this guy. I rho naught by 4 by x. You need dE by dx. So I rho naught by 4 pi minus 1 by x square. Yeah, substitute there and you're done. So I rho naught by 4 pi x square. So this is the charge per unit volume. So this conductor, right, will actually have a charge distributed throughout. It's not neutral. Clear with this? If you had a uniform resistance, even then you would have still had a problem because, the field is getting messed up as function of x. If the field was uniform, then you won't get any charge inside. Clear with this? I hope you can see how much we played around with this question. Like, this question can be asked in thermal conductivity, capacitors, current. See, we can see voltage. I can ask you the charge per unit volume. This thing comes from Gauss law. So that you can keep playing around like this. Clear with this? So this is what I was saying. Every day, if you do this level of questions, even 10 to 15 per day for physics, it is sufficient. But you have to take time. If you're doing 15 questions like this, and each question you're spending 15 minutes, right? I think that's almost 225 minutes. That's almost 4 hours. It is worth it. Then you're sitting and doing some random stuff, right? So, and you can. So maybe if you can do, maybe you have a lot of good content. The GRSC thing, you have material. If you're done with GRSC and that Fijika sheets, you can ask me. I can send you more. Right? So class notes ka revision, advanced notes ka revision, all these questions, right? See, all these questions I'm teaching you, right? Aapko lag raha hai, haan, ho gaya. You take out the notes tomorrow and try to do this again. Trust me, you will get stuck. Currently, you're feeling like, oh, we understood. You understood, but trust me, the problem is not yours. The problem is not yours. You have to take a rough paper and try to solve each and every step till you get the answer. Do this tomorrow. Trust me, do this tomorrow and see. You will not get half the problems. You will get stuck somewhere. You will start scratching your head like, yahan pe kya kiya tha? Problem kya ho raha hai na? You're trying to remember what it did. You're not trying to figure out on your own how to solve. So please do resolve the notes. Then the problem becomes yours. By the time we'll finish our advanced revision, I think we will have a bunch of it. So you want to use dV is equal to minus, actually, Akash, that also works. That also works. You can, the field, you can do that. That works. Clear with this? So that is one. Then, great. Then there was this one. We have a big infinite plate. small thickness D. So there are 4 points here, A, B, C, and D. Distance between them is L by 3, L by 3, and L by 3. Then what you did, you started sending current here I, and then you started pulling current I from here. Doesn't matter how it is being done. Someone is sending current I from A, and the current I is coming from D. Remember, this is an infinite one, okay? It's a big plate. I want you to find VB minus VC by I. What is this value? A, B, C, D are in a single line. Collinear points. There was something similar like this in one of the JEE equation. Modified it a bit. Resistivity rho. See, V is equal to IR is 1, J is equal to sigma E is also called as, microscopic Ohm's law. This is the more fundamental thing. J is equal to sigma E. So, if you remember, J is equal to sigma E, where it came? Semiconductors. Conductivity of holes, conductivity of electrons, mobility of electrons, mobility of holes. अभी मेंस आ रहा है वापस तो at least वो those topics थोड़ा रट्टा मार के जाओ. Yeah, if you have not scored 99.9 percentile, you should definitely prepare little for mains and go. Don't underestimate it because bits के लिए भी same portion है. You need to put bits में at least 300 plus to secure a seat in bits Goa में CS at least. Last year cutoff तो थोड़ा कम था because last year papers were tough. This year never know what would happen. So you should have a bits as a good backup. Trust me, it will give you a lot of confidence. When I wrote my advanced exam, right? I wrote the bits exam like 3 days, 4 days before the bits exam, a bit before the advanced exam. I actually placed it that way. I can choose any day. I placed it 4 or 5 days before the advanced exam. So the idea was this. I went to the exam, I wrote the bits exam, and the best thing about bits, the score comes out immediately, right? Once you write the exam, you know the score. The score comes on the board, how much you scored. And I scored around 404. You can do extra questions also. That time it was 150 questions ka paper tha. So 150 questions, and if you attempt all 150 questions and submit, you get extra 12 questions. It is still there. I hope you guys know that. So for you guys, it is 130 questions. You have to write all 130 questions and you have to submit everything. And you still should have some time left. Then you'll get an option on the screen. Do you want to solve extra questions? If you do only 129 and submit, you won't get that option. So, and that 12 extra questions will be 4 maths, 4 physics, 4 chemistry. So I did 150 plus 12 extra questions. I think it's close to 400 score. So once I saw the score na, the first thing that went into my mind is, abhi advanced jo bhi hoga, bits पिलाने में मेरा computer science seat backup hai. You're getting it? And that helps a lot because when you go to the exam and you're panicking and getting tensed and you feel like, the world is ending for your life, kya ho jayega? The thing comes to your mind and say like, boss, kuch nahi hoga. Advance kuch bhi ho gaya abhi, fir bhi right, mera backup to hai. Right? So let's forget about what bad can go. Let me focus on the exam and give my best. And that is the reason in the advanced exam, I was very cool. Matlab, the entire paper, right? I had never panicked. I panicked in the last paper, chemistry, because I need to go to washroom. And there was a lady newsletter, and I was feeling shy to ask her, like, how can I ask and go in the middle of the exam? That is one nonsense thing I did. But luckily, it was chemistry paper, so time tha. Then I said, yeah, boss, I had to go. I wasted around 15 minutes there. So the washroom was in the first floor, I was in the third floor, I was walking, running, and also. I think that was the only small goof up there, but yeah. And the goof up was because afternoon, right? Lunch I ate little. It was very hot, so I drank orange juice. Then I felt I was sleepy. Then I drank coffee. Then I felt thirsty, so I drank lemon water. अब इतना पीने के बाद तो washroom जाना ही पड़ेगा. So that was the big goof up I did before that last paper. So yeah. How do we do this thing? See, the idea is again, the moment you hear the word infinity plate, right, and current I is going, current is coming out, you should got an idea, boss. It's the principle of superposition jaisa lag raha hai, right? So what we do, again, same story. Imagine only current I is flowing through A. Then how will the current distribute? The current will actually distribute like a circle thing, isn't it? It will keep going like this. So if you take at a distance x, the current density due to A, that guy will be I by 2 pi x into d thickness. You know, where is the current flowing here exactly? If you take out the thin disk, the current is coming out of this, isn't it? It's a thin layer. So current is flowing out through this surface area. How much is that surface area? 2 pi x into d. Making sense? It's like a surface area of a cylinder. Sure with this. Now, when you see from both of them, so I'll just draw the top view. So this was A and this was D. So if you take at a distance x, so because of A, the current density will be I by 2 pi xd going this way. And because of this guy, this distance will be L minus x. So this guy will be, the current density to D will be I by 2 pi L minus x into D. So if you do both of them together, the current density will be I by 2 pi D 1 by x plus 1 by L minus x. Clear with this? So if you send a current and pull the current, this is the current density as function of x, where x is the distance from A along the line AD. Actually, if you see, right, the current is flowing in all random directions and reaching D. It's just going randomly everywhere. We cannot find that, but I can find along the line AD. Clear with this? And we know J is equal to sigma E, which is E by rho. So indirectly, I got the field. Then you're done, right? So VB minus VC is equal to integral minus E dx. Limits will go from B is the final thing, so L by 3 to 2L by 3. Substitute there. आ जाएगा BB minus VC by I. Are you clear with this? So the main idea was that. So when the current goes there, the current will distribute something like this. It is going in circle, 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 circle. It is spreading out. So when you send a current through only one, but if you send through both of them at the same time, the current flow will be pretty weird. It must be the center line is going straight, but everything else is making all weird turns and all. So you can't draw that properly. But is the idea clear, everyone? So you can play like that with the current density J. Right, we will see more of that on that also next time. So that was one. Let's do one question more, and then again, this is just a standard model. I just want to see how will you handle this. C, 2C, 2C, and 3C and C. Can you find C equivalent? This is not a Wheatstone bridge. There is no diagonal symmetry also here. So this is a type of a question where it is brute force solving. Generally, they don't ask. They don't touch these things. Yeah, but I want you to know the process. If at all they want to ask this, they'll put a C here and they'll make it symmetrical for you. But let's say it is still 3C. And you will find a lot of, other techniques you have, like, what is that? Star, delta, and all that stuff. So I don't like that. But if you are convinced, you are comfortable with that, you can use it. Right? I just stick to two techniques, Kirchhoff's junction law and Kirchhoff's loop law. That's it. I don't want to go to the exam, see the question and I think like, should I use method A, method B, method C, method D? That itself will eat away half of my time. Better chup chap take one method and get so used to one method, your speed comes from there. There's no point in learning 10 methods for one question right now. Done. Like right now, your job is only to solve as many models as possible on your own. whatever doubts you are getting not cleared, should try to clear it on your own, because exam and one will be there to help you out. And again, don't write it too many. Like per day physics, I think if you do 10, 15 quality questions, or and maybe some, if your subject is weak, then maybe notes and maybe 10, 15 questions. Your notes is done thoroughly, then I think 30 questions per day would be great. 30 would be a good limit, good number for physics. So what is the idea here? Assume a battery V, junction law, this is what we do. Assume this is 0, this is V, this is X, and this is Y. Right, so assume the charges are flowing here. Let this be Q1, let this be Q2, and let this be Q3. Let this be Q4, let this be Q5, and let this be in Q6. It doesn't matter. Q5 is equal to Q minus 3, but yeah. Now when you take a junction X, the net charge flowing through a junction must be 0. So what is the Q1 plus Q2 plus Q3 is equal to 0. What is Q1? Potential difference, capacitance into potential difference. So C into V minus X. What is Q2? 2C into 0 minus X. So remember, charge flows from higher to lower. You have drawn the arrow this way, means you're assuming charge is coming from 0. Then C into Y minus X is equal to 0. When you write at junction Y, Q4 plus Q5 plus Q6 is equal to 0. This is V minus Y into 2C plus Q5 will be C into X minus Y. You can choose the direction of arrow however you want. Doesn't matter. So 3C into 0 minus Y. Two equations, two unknowns. You'll get X and Y from here. That itself is another equation. And then what is the charge flowing through this thing? If you see this is Q1 and this is Q4, that means from the battery you're getting charge Q1 and Q4. Therefore, C equivalent must be the charge from the battery, which is Q1 plus Q4 by V. Clear with this? Yeah. Now solving equations takes time, but if you see this process, right, how to do should not take more than a minute. All clear with this? Now, I'll give you some homework questions. Try them. So next class when we meet up, we will discuss them. So we have a Q1, radius R1. We have another Q2, radius R2. Distance between them is L, which is much, much greater than R1 and R2. Right? So at any random point in the space, if you see, this is your E1 and this is your E2. These are the electric fields. This is a good one. Huh? We will again see something like this in magnetism also. I want you to find, so E1, E2 are electric fields in the space. Find integral E1 dot E2 dV is equal to. Find the value of this. So I hope you remember this. You have gone through the notes you would have seen. Later on, magnetism is dekhenge. You'll have integral B1 dot B2 dV. So this is for the whole region. So from the shells to infinity. dV is your small volume. So E1 and E2 are the electric fields due to the two shells. And when you do dot product and multiply with dV, what does the value give you? So you have to think about that. What does it give you? That was one. And this is, we have a cylindrical capacitor. Right, sealed at the bottom. It's a pretty long capacitor there, L. This is A and this is 2A. You're connecting a battery between this and this, V. The space between them is filled with a liquid. Density rho. Dielectric constant K. Right, now what you did, you made a small hole here. Area A. And this liquid started leaking out. Fluid mechanics. So your picture would become something like this after some time. Find the time when the liquid stops flowing. Meaning your final picture will look like this. Something happens here. After some time, right, the liquid will stop coming out of the hole. So this is how the picture will be. X. Find x as function of time t. X is the height of the liquid as function of time t. A simpler question would be this: find the final x. The whole tank does not become empty. It remains in equilibrium for some reason. Getting it? And you can take this L is much greater than A. So all the fringe effects you can neglect. Initially, it is completely filled till L. Clear with this question. So as the height of the liquid is decreasing, something happens. So you need to figure out what is happening there. Yeah. That was one. Then this is there in the class notes, but please give it a try on your own. It's a pretty good one. We have a shape like this. This was theta. This is radius A. This is D. Again, A is much greater than D from the fringe effects. This is length L. This is angle theta. So the terminals are connected here. This is A and this is B. So if you see the top view, it looks like this. It is a part of a piece basically. This is the top view. This is A and this is B. Find R equivalent. Find J as function of X. Resistivity is rho. Find the drift velocity of the particles as function of X. You can take whatever you want. N is the number density, number of electrons per unit volume. And now something happens here. Because these electrons are going, along the circumference, you start getting a charges induced. So there will be a potential difference here. This is also called as transverse voltage. Because I'll tell you an idea what is happening there. When these electrons are rushing here, they will have a centrifugal force mv square by x. That centrifugal force, electrons are going outside. So because of this, electrons will accumulate here and this becomes a positive charge. So because of that, you get a voltage along the radial direction. This is called as transverse voltage. Right? So that is V inner minus V outer as function of x power n. Find n. Definitely give it a try on this thing. Right? This question I'll not be discussing. So try if you're not getting it, and then go to the notes, check it out. If you still don't understand, I'll still explain you, but it's really a good worthy question to try. So transverse voltage. Right? So that is one thing you should try. Then we had few more things. These are capacitor-based questions. So we have a battery B here. This is C. This is 2C. This guy was minus CV. This is plus CV. And let's say this is empty. Find the heat produced when the switch is closed. We will do questions like this in the next class also. We have a resistor R. This is C. This is 2C. Let's say this is plus Q. This is minus Q. This is a minus 3Q. This is plus 3Q. So when you close the switch, find the current as function of time t. Yeah, try these questions, right? So when we catch up on Wednesday, we'll continue from here. We will do a few more varieties. So this thing maybe we can discuss a bit. I will discuss them a bit, but this third question, check out from the notes. But if you're still confused, I'll discuss. These are okay. These are like, this is still a decent question. This is a standard question. I just wanted to show you that, these two capacitors are not in series. I hope you should know that. Just because you're side by side does not mean you're in series. But two capacitors to be in series, they should have same charge or same charge distribution, same charge there. We will see something like that in the next class also. Okay, take a break. Come back by 8:45. We'll start the test at 8:45. Go have your dinner, right? Relax a bit. So any doubt in the class notes, you can ask a bit. If you have one or two, if you have more, you can wait back after the exam.
Sir, I had a doubt in today's